There we go. Okay. So I did a detailed analysis of every instance of every problem that occurred on the tests that were taken yesterday, which is a pretty good sample, pretty good statistical sample. Gives me a pretty good idea exactly where people are having some issues. And so what I want to do are two things today. The most important thing is I've captured some examples of those questions. I want to briefly address those to see if we can kind of kick you loose and see if we can, there's some kind of an issue conceptually or mathematically that's causing you to stumble on this. So let's figure out what is it. All right, so something like this. There's this graph could look a trillion different ways, but on the test, but this is just one example of the kind of question that deals with this. So use the graph to answer the questions about existence, limits, and continuity. All right, so does f of -3 exist?
Yes.
Yes, it does. Absolutely.
So it does because
It does because it's graphed there, right? So what is our test for existence? Existence just means, is the function defined there? Do I have to draw something at that point? Is my pen on the board or off the board when x equals -3? It's on the board, right? So it exists. Okay. Does the limit of f of x as x approaches -3 exist?
yeah.
It does.
Because it approaches from both ways.
Yeah, it does, because from both sides, exactly. As an ant approaches from both sides, he anticipates stepping on the same place, right?
Mhm.
Okay, very good. Does the limit of f of x as x approaches -3 equal the value of f of the function at -3?
No. Yep.
Yes.
Wait, why?
It does.
How can we just say
Because
no?
the limit, wouldn't you agree, and let me draw a picture here, the limit is right there, right? And, I'll say it again. No, that's as x approaches -3.
Oh, but the y is 2.
Oh, okay, so the value of the limit is 2. You're right.
Okay.
So the value of the limit is actually equal to 2. Well, what's the value of the function there? 2, right? In other words, the ant actually would end up stepping exactly where he thinks he's going to step. But the limit, remember this, and people, this is the thing that people just automatically tend to forget about limits as they get away from them a little bit. The limit has nothing to do with what actually happens at -3, right? At x equals -3. It's only what's predicted to happen at -3 based on the function, right? Yes, ma'am.
Will you answer those 4 questions, but using like as x approaches just 3?
Yeah, and we'll do a different one too,
Oh,
right?
okay.
We'll do a different one too. So then,
Wait, what was
so
that?
is the function continuous?
Yeah.
Yes, it is, because both of those equal the same value, right?
Okay, wait.
Okay, make sense?
No. Number
So-
3 was yes.
Yeah, these are all yes. Yes. Okay. Now let's pick a different value. Let's pick one maybe that's a little tougher. Was there any other questions on that? Okay, we're good there. Let's pick a value like -2. So now instead of saying -2, instead of -3, it's -2 instead of -3. So every place it says -3, ignore it and substitute in your head -2. Okay. Does f of -2 exist?
Yeah.
No.
What?
No, it does not, because there is an open circle there, right?
Open circle does not exist.
Right, open circle means that's a hole in the function, right?
Got it.
Okay, so it doesn't exist there. So that answer, if that's a -2, that answer is no. Does the limit of f of x as x approaches -2 exist?
Yeah.
Yes.
Yes, it does. It does. What is the value of the limit? 3. Right. The limit of f of x as x approaches -2 is equal to 3 because the ant thinks he's going to step right there,
Okay.
right? So then, does the limit of the function as x approaches -2 equal the value of the function at -2?
Yeah.
The function doesn't even exist.
So
Right. So the answer is no, right? Because the function doesn't exist at -2. And so then, is the function continuous at -2? No. Right?
Okay, yeah. Wait, why is it not?
It's not continuous because in order for it to be continuous, remember our discussion of continuity at a point, Remember what has to happen. The limit has to exist, the function has to exist at that value, right? At that point. And the two have to agree, right?
So the last question
Mhm.
is like a tricky because if the first two aren't both yeses, then it's a no.
Exactly. Okay, well, let's do one more though. This is one more. You're right.
Number two.
Okay, one more though. This time we're going to use +3.
Yeah, let's do
Okay.
that.
So now that's easier. I can just make those all plus signs. So +3. So does f of 3 exist?
No.
Yes.
Yes, it does.
Okay, raise your hand if you say yes.
Oh, Lord almighty.
Raise your hand if you say no. Now put it down real fast because you're wrong.
Oh.
What? So it's yes. How come?
Because there's a circle.
Yeah, there's a dot.
That's
Okay. So what is the value? What is f of 3?
Two.
It's 2. Exactly. Okay, does the limit of the function as x approaches 3 exist?
Yes.
It does. The ant thinks he's going to be there, doesn't he? Right? So what is the limit of f of x as x approaches 3? 4.
Wait, okay.
So he thinks he's gonna sit there, but really he goes down there.
Right.
Okay.
Right. And the limit, remember, is only, it's not what actually happens, it's what the function predicts is going to happen. Right?
So the limit of this is 4?
Right, because think, as the ant walks along from the left or the right, and you say, where do you think you're going to step, buddy? He's going to say, oh, I think I'm going to step at x equals 3, y equals 4.
Okay.
Right? When he actually steps there, lo and behold, he ends up on this isolated point. But he doesn't know
Oh,
that.
but that's where he thinks. Oh.
Yeah, right? So the limit, you kind of get what I mean then when I say the limit is where he anticipates stepping. The value of the function is where he actually ends up. So then, do those agree? No. So because they don't agree, is the function continuous?
No.
No.
Oh.
We got it. That's it.
Wait, so if it's an open circle, it's not contingent?
If it's an open, you're right. If it's an open circle, it's not. And we can also see that because what was our pen on paper or pen on whiteboard definition of continuity? For it to be continuous, I have to be able to start here and end there without picking my pen off the board. Any place I pick my pen off the board is a discontinuity.
Even if it's a little circle, that's taking it off the board.
It is, because technically I have to do this,
True.
right? Now leave it on the board, take it off the board, back on the board. See what I'm saying?
That's the discontinuous function.
So it's discontinuous. It's discontinuous there, and there.
And the bottom.
Well, and then right there, I suppose, too, yeah.
If it was something like -5, it wouldn't have been discontinuous though.
Right,
Wow.
Can we do an end?
How
Because
Right.
It's a filled in dot.
that's right. That's a good point.
But it's the endpoint.
Yeah, that's right. But remember what we said about the endpoint? We said that endpoints only require a one-sided limit. For a closed continuity on a closed interval, it's going to be continuity on the open interval plus the one-sided limit at the endpoints. Right? It was, and I'll tell you, and make a note of this. This is, if you have a question about that, that is in your book there's a very important part of your book on page 70. Definition of continuity on a closed interval, page 70. There's a blue box there that defines that we went through in class. It's also on the video stuff.
Got it.
All right. Moving on.
All right.
Okay, stuff like this. This was one. It came up quite a bit. And I get it. This is kind of a weird one, but we have a strategy for this. We have a very clear strategy if we have, if we want to give an extended function. What does that mean? Let's discuss that just a little bit. So an extended function that's continuous at the indicated point. Is f of x, as it's currently written, is f of x continuous at 4? No, it's not. Because if I try to evaluate the function at x equals 4, I get what?
0.
0 over 0, which means what in terms of the function?
More work.
And it means what else, Clancy? Hole in the function. Right, exactly. If I have a 0 of the numerator that's also a 0 of the denominator, then that means we get a hole in the function. Good. Okay. So there's a hole there. So if we want to fill this in, what do? Well, we've got to, go ahead, say it again, Alexa. Right, we've got to get rid of the indeterminacy. We've got to figure out, if we want to fill in that hole, we've got to figure out, okay, what's the limit of the function there? Because the function doesn't exist, so we'll find the limit of the function, and then we'll just assign the function that value at that point. Does that make sense? Okay? So we've got, in other words, remember this terminology we used in class, and it's a little bit awkward, but this is the way math textbooks and mathematicians talk about it. We need to find another function that agrees with this function everywhere, at all places but one point. We've got to fill in the hole, in other words, right? So if the limit of x minus 4 over, well, we don't even really have to do this with a limit. You know what, let's not do this with a limit. It's not strictly necessary. If this is f of x, we can do this a little more cleanly. If f of x equals x minus 4 over the square root of x minus 2, then we're going to define a new function. Let's call it g of x. Okay, so g of x equals x minus 4 over the square root of x minus 2, but we're going to do some algebraic cancellation. What do we multiply top and bottom by here?
X conjugate. Square root x plus 2.
Good. Okay, so we're going to multiply by the conjugate of the bottom in this case, the conjugate of the expression that has a radical in it, right? So the square root of x plus 2 over the square root of x plus 2. Okay, and if we do that, we get what on the bottom? This is important.
X minus 4.
X minus 4, and that's because of the conjugate pattern. Because we've just, all we're really saying here is, this is just a disguised way of saying A, pretend that's an A and that's a B. There's A minus B times A plus B, and we know that A minus B times A plus B, that conjugate product pattern gives us what?
Equals a squared.
Yeah, difference of squares, right? So that gives us then, on the bottom, it gives us a squared, which is x, minus b squared, which is 2 squared or 4,
Sweet.
right? On the top, we get this big mess, but that's okay, because we can algebraically cancel those factors. Now you're starting to get some intuition here, and this is really, don't just do this mechanically, connecting the dots. I want you to think about, just try to make this connection. Eventually, if you keep thinking about things like this, eventually they become very clear. What did we do there? Well, we did something pretty cool. We did something by algebraically canceling factors. We haven't changed the behavior of the function at all, because all we've really done is just, divide by 1, right? Okay, but we have eliminated a restriction on the domain because we no longer have a 0 in the bottom. That's a really cool concept, right? We didn't change the shape, but we eliminated a hole. And so what's our new function going to be then? What is, in its simplified form, what is g of x? Well, no, it's that, right?
Wait, we don't have to plug it in.
Nope, that's not what they're looking for in this case. What they're asking for is the extended function. So we want the function that agrees with our original one every place except also fills in the hole. Okay?
Why is this on graphing?
Why is it on what?
The graphing section.
I don't know. I just put it in there. It's the ones in the graphing section. A lot of times I'll throw stuff in the graphing section where you don't need a graphing calculator. You don't need one for this. But I just, keep in mind that I'm just trying to kind of keep the two sort of roughly on the same scale. So one doesn't have 9,000 problems and one have 2 problems. So sometimes I lump stuff in there where you don't need it. So, make sense?
Yeah.
Okay? Stuff like this, okay? So this is essentially all very, very, very similar stuff, right? We want to find, is there a point of discontinuity, yes or no, and is it removable? Okay.
This would be.
Don't you? Oh. Fine, sorry.
Where'd it go?
I'm not gonna graph.
What? It's really, what happened? Yeah. There we go. Okay, so let's look at this. We want to know, is there a point of discontinuity? All right, so
Yes.
so what is the value of the function? How are we going to know? I'm gonna stop talking. You tell me. How would we know if there's a discontinuity?
So -1.
Okay, so well, this is a piecewise function, right? So we have to interpret this as a piecewise function. Boy, that's kind of blurry. Huh. The function on top is that is the function where the domain includes all values except -1. Every place except -1, that is f of x, right? The bottom one, when x is actually equal to -1, the function assigns the value 4. Okay? So what are now let's think about this before you try to jump into the math. I really believe in calculus and physics and highly analytical classes like this, it's better not to just jump in. Just pause for a second and think about this. Now what's going to happen if this is discontinuous? What's going to happen? Okay, there's going to be a hole, and the point that the function assigns will miss the hole, right? Does that make sense? If it's continuous, on the other hand, the top part of the function has a hole at -1, but what if the bottom part fills in the hole exactly? Then it makes it continuous, right? Everybody see that?
Yeah.
So we just have to answer that question. Does the bottom function fill in the hole properly, right? So how would we know?
Oh, plug 4 in.
Plug 4 in, and really what we're doing is we're taking a limit, aren't we? Right? We're taking the limit of the top function to see what's the value that the ant approaches when he walks along the function towards -1. And if that value is 4, then that fills it in and makes it continuous, right? That's really all we're doing. And if it doesn't, then it's discontinuous. Then the hole
At
misses,
-1.
right? So we can do that easily, right? We can just say the limit of f of x as x approaches -1. Well, if I'm approaching -1, am I at -1? No, so I'm on this part of the function then, right? Equals the limit of 1 minus x squared as x approaches -1, which is what?
-1.
Yeah, 1 minus -1 squared is 1, right? So I get 0. And so the limit does not match up with the value of the function, right? The value, the hole's too high. It's supposed to be at y equals 0 and it's at y equals 4. So is it continuous? No, it's not. It is not continuous, but then the other part wants to know if it's discontinuous, is it removable or not
But
removable?
what's the point of discontinuity?
The point of discontinuity is going to be, well, the point of discontinuity is at x equals -1, right?
So it's always negative, it's always that number.
Well, yes, right, because that makes sense. Does everyone understand the question? Where's the point of discontinuity? Well, what if the ant's walking along the top function? Are there going to be any discontinuities in the function 1 minus x squared?
No.
There aren't. And let me remind you why there aren't. Because the only places where discontinuities can occur without having a piecewise function, but if we're saying if we're only going to be on this part of the domain, then it's defined every place. The only places where you could have a discontinuity is if you're dividing by 0 or taking an even root of a negative number. And I'm not doing that. That's just a nice, easy function, 1 minus x squared, right? So we're fine there. The only place where we could have a discontinuity is going to be here, right? Okay. And we do. We do have one. So it's at x equals -1. Now, is it removable or not?
Yeah.
It is removable. How come? Somebody tell me, why is it removable? Because it's just one point. That's our definition. A removable discontinuity is one that can be repaired by either adding or moving a single point. We know it's one point because the function is defined every place else, right? So if I were to graph this, we can see what the graph would look like. The graph would just look like 1 minus x squared is just going to look like, let's see, where are we at? We're at -1. So it's just going to look like 1 minus x squared. So we're just going to look like this. We're just going to look like right? Only our function is not defined right there. Right, we've got a hole there in the function, agree? And the function is assigned, whoops, supposed to be red. The function is assigned the value when x equals -1, y equals 4. So 1, 2, 3, 4. So it's right there. You missed it. But that's easily repairable. All I've got to do to repair it is just grab that guy and push him down there. In other words, could I easily define a function that would? That's really what we're saying when we say, is the function, is it a removable or non-removable? It's removable because it's easy to do. All I have to do is just change the function. Couldn't I just do this and fix the whole problem here if I just said, oh, no, don't make that a 4. Instead, let's just make it a 0. Now we're set, right? It's easy to do. Now, if it were non-removable, that would mean I'd have two functions that did something like this. There's one and there's the other. To fix those, I've got to completely abandon those functions and change them for new ones, because I have to change an infinite number of points.
So it's not removable?
Say it again?
Not removable because why?
No, it is removable.
Oh.
It is removable because
No.
redefining the function at the point of discontinuity to be equal to 0 would remove the discontinuity.
No.
Oh, this one would be non-removable
Because one-sided limits are this.
because the limits don't agree. Right, I mean, there's
So
a
they're
break in that
different.
function, yep.
I don't get that.
So do you understand why this problem has the answer it does then?
How are one-sided limits the same? Like, what's an example of that?
Of a one-sided limit?
That are the same, they aren't ever the same, though, are they?
Well, here's what we can say about, remember, and I want you to think back a little bit. What we said when we started talking about one-sided limits was, okay, that really helps us out because now this improves our definition of a regular limit. We always said from the very beginning that a limit exists if ants approaching from both sides agree on the same destination, right? With one-sided limits, now we can say, okay, well, in other words, the limit as x approaches, call this c, x approaches c from the left is the same as the limit as x approaches c from the right. If those two one-sided limits agree, isn't that the same thing as saying the two ants agree, right? And so really a two-sided limit just means that the one-sided limits exist and agree, okay? And we'll see another example like that too. All right, I better move on. Let's see here. Let's just take, we can come back to this one if we need to. This is really similar to what we were just talking about. Okay,
Oh, I love these.
okay, so these, I think we can come back to this too. I kind of, what I did was, I looked at all the graphing calculator ones that people had trouble with first in decreasing order of importance. So now we're getting into ones where most people were okay and there were just a few. So we'll come back to this. I want to scoot forward and go to the
Wait,
non.
what about the one where it's like, where is this, like, something? And it was like negative cotangent x.
That's in the, yeah, that's coming up.
Oh, you're
That's the non-graphing test, yeah. So here's the non-graphing test, okay? On the non-graphing test, this was one that was this was a loser.
Well, yeah.
A lot of people missed this one.
taking
Oh, I
out.
wrote down all the answers.
So let's look at this. Use the graph below to determine whether the statements about the function are true or false. So is this true or false now? Look, can everybody see this?
Yeah.
Okay, so true or false, the limit of f of x as x approaches -2 plus, meaning -2 from which direction?
Right.
From the right, is equal to 4.
Yeah, true.
Okay, the limit as we approach -2 from the right is 4. That's correct. That's correct, good. Okay, so true, good. So that part wasn't the one we missed, I guess. True or false? The limit of f of x as x approaches 0 minus, so 0 from the left, is 5. False. What is it?
Zero.
It's 0. Very
How do you
good.
know?
It's not 5. It
There's
should
a
be
point.
0. Okay?
But there's also a point on 5.
But there's
But the limit is what is the function? What value does the function approach? Okay? So, true or false, the limit of f of x as x approaches 0 from the left equals the limit of f of x as x approaches 0 from the right. True. And both of those are equal to 0, right?
It's the last one that gets.
Oh, okay. Gotcha. Okay, true or false? That was the last one. True or false? The limit of f of x as x approaches 0 exists.
False.
True. If this is true, then this one has to be true. That's the definition of a limit, right?
Okay.
If the two one-sided limits agree, then the two-sided limit exists. That's the whole point of the one-sided limits. Yeah.
So the only way the one we just answered didn't exist if there was like vertical asymptote or
Yeah, or if it was like this or something. Yeah, exactly. Breaking the function. Okay, so true or false? The limit of f of x as x approaches 0 is 0.
True.
True.
What?
Because as x approaches 0,
It's going to 0.
now listen. As x approaches 0, doesn't the ant think he's going to step on 0?
Yeah.
Right?
Just said this.
Does that make sense, Alexis? Does that make sense?
Yes, I just explained. She's gonna go.
Oh, okay, all right.
Wait,
Okay.
he thinks so. That one's just
But-
he thinks
but-
he's gonna step there, so he
Okay,
does.
so if it wasn't the limit, it was just f of 0 equals 5.
Right. Okay.
then it wouldn't
Yes.
exist.
Right. Good. So that's different from, and I think they asked that probably down here. I keep going. No, they don't. But what is not the limit? What is f of 0? 5. Good. Yeah. Good. Okay. Keep going. True or false?
The limit of f of x equals 4.
Yeah. The limit of f of x as x approaches 2 is 4.
False.
False. Okay. Why?
Because of that last one.
Okay. Right here. Ellie, you got the floor. How come?
Because they're not coming together at the same point.
Exactly, because, now listen closely, because the limit, this is false. The limit of f of x as x approaches 2 does not equal 4. That's not true. What is true is that the limit of f of x as x approaches 2 from the left is 4,
Oh,
right?
gotcha.
An ant walking from the left would approach 4.
But there's a break.
But there's a break. An ant approaching from the right. So the limit of f of x as x approaches 2 from the right would be what?
0.
0. They don't agree, and so the limit doesn't exist.
True.
Okay? Right?
How did you get 4? I thought you couldn't.
Well, because as we walk along the function from this side, the limit just asks us, based on the function, where do we anticipate being when x is 2? As we approach from the left, we think we're going to step right there.
Oh, okay.
Right? The limit doesn't care where we actually step. It's just where do we think we're going to step, right?
Not to the right.
From the left. From the right, the ant would be walking along this flat spot and think he's approaching a y value of 0. It's irrelevant that that's the right answer. That's where he actually would step. We don't care. The limit doesn't, as far as the limit's concerned, irrelevant. Okay, but because they don't agree, the two-sided limit, the regular limit, doesn't exist. Okay, because the one-sided limits are different. All right. So, true or false? Last one. The limit of f of x as x approaches -4 is 4.
False. Wait, are you sure that's true?
Okay.
4 from the left.
Oh, from the left. Sorry. Yeah, 4 from the left.
No.
There is no left.
No, there's no left, so it's
Oh, wait,
false.
I know. Now there is a left.
No.
Yes.
There is,
It's false, but it's false.
but it's false.
Because it's an
Because as the ant walks towards 4 from the left, he's approaching a value of 0. Not 4,
Oh.
right?
So just to refresh,
Yeah.
positive is this way.
Yeah, think the x-axis. The positive direction on the x-axis is that way, negative is that way. So if I'm approaching 3 plus, it means I'm approaching 3 from the positive direction.
Somebody
Okay.
heading that way.
From bigger numbers. Yeah. So I'm walking backwards. Yes, I'm approaching from the right. So let's get that straight. So if I'm approaching the limit of f of x as x approaches 3 plus, means I'm putting in numbers like 3.1, 3.01, 3.001. I'm approaching from that direction, not in that direction.
Wait, so draw it with your pen on the graph.
Okay, so I would be doing this. So if I'm approaching 3, I would be doing this. I would be going in that direction.
You're going back.
Back towards 3. Okay, there's too much talking. Everybody listen, because this is. I understand why this is confusing. You could interpret that in 2 ways, and one of them is wrong and one of them is right. You could interpret it to mean I'm approaching 3 moving in the positive direction. Wrong. That's not it. I'm approaching 3 from, I'm approaching the value of 3 because that's what we do with limits, right? We're approaching a value. I'm approaching from values greater than 3. So I would be walking from right to left along the function towards 3. Right. We call this a right-handed limit because we're approaching from the right towards the value. Okay? It's easily confused. And so approaching 3 minus would mean I'm approaching from the negative direction to walking left to right. Okay? This one, okay, I'm not going to go through the whole thing. What's the trick?
You times the top and bottom by x plus 10 plus square root of 10.
Yeah, square root of x plus 10
Yeah.
plus square root of 10.
Yeah.
You multiply top and bottom by the conjugate expressions. Yeah, and it'll work out if you do that. It's guaranteed to work out. Okay? There's good examples to look at. Okay, stuff like this.
Bad stuff.
This stuff.
What is it
Take
approaching?
it off.
I hate that.
Let's say we're approaching pi. Okay? So what's going to happen here? So what do we do with stuff like this when we have cotangents and
Yes, that.
sines and cosines? Good. Okay, we rewrite this in terms of sines and cosines so we can simplify it, right? So this is going to look like the limit of, and that's a phi, who we call that? Phi times cosine over sine. One over, oh, I think I messed that up then. What I really wanted to do with this. Okay, hang on a second. I think I messed this up. I wanted this to be a tangent.
So it did cancel out.
Yeah.
It's nice.
Yeah, I wanted this to be a tangent, for sure. So let's go back.
So now
Change your notes, change your notes.
sine over cosine, yeah?
Yes. Okay, times 1 over sine.
Yeah.
I'm gonna figure all of this over the weekend.
Okay, so what, and this is as theta, or as phi, sorry, as phi approaches pi.
Pi.
Phi, pi, faux, fum.
I know that's what I was
Oh,
thinking.
don't you think?
Yeah.
Great minds think alike.
I'm thinking phi as it approaches foe.
Okay.
It's funny.
So what can we do here?
You cancel the signs.
There you go. Cancel the signs. That makes things a little simpler.
1 over cosine, which is secant. Yeah?
True.
Or is it not?
It is.
But it's pi.
So it's pi.
Pi cosine. Plus 0. Yeah, you're right.
Okay, so now what?
Well, negative 1.
Yes, yeah. What do we got?
value of cosine of pi.
Okay, good. So we're going to directly evaluate.
Why
Good.
is there a B or whatever on the top?
Because it was there from the beginning.
Oh.
Okay? It was just, so we had, this is going to sound a little funny, but what I would call that is a naked phi.
A naked phi?
Because it's not clothed inside another function. So it's one just by itself. Seriously, that's what,
So the answer is.
people are laughing at me, but that's what you could call that.
Okay.
So,
It's negative 1.
so the answer, yeah. So look at this now. Not negative 1.
Negative pi.
Negative pi, because this is 1, and here I think is the trick on this. This really isn't that hard a problem. I mean, if you just resolve this into sines and cosines, things cancel. But what people want to do with this, because they're so used to having zeros over zeros, they want to make this into a 0 over 0. It's not. I can evaluate this. If I plug in pi for phi, I get pi over cosine of pi is negative 1, so I just get negative pi is my answer.
Wait, cosine? So we look at our chart,
Mhm.
and we look at what cosine is at pi.
Yep.
So on our
That's
little
pi.
thingy, right there. And
Negative
cosine,
1.
yeah, okay.
Okay.
Yeah, okay.
Make sense?
Yeah.
Okay.
Totally.
All right, moving on. Okay, this.
Oh, I think I, yes, I do.
Yeah, I think we're
Easier.
kind of, you can see where people, I mean, this makes sense. You can kind of see where people had trouble. Their problems sort of like this. We've dealt with some, let's do one more. We've done a lot of them like this. So what's the limit? As c, if we let c equal 3, what's the limit of f of x as x approaches c, which is 3, from the right?
The first one.
So that's going to be, now which one of those two functions would we be?
0.
Yeah. Just kidding. I know what I'm doing.
Good, it'd be the bottom one. How come?
Because it's bigger than three.
Because it has to be bigger
Right.
than.
Greater than 3.
Okay, because x is greater than 3 on the bottom, right? And so if
Yeah.
we're approaching from values greater than 3, we have to be walking on this part of the function. So all we do then is we just evaluate the limit of x over 3 plus 1 as x approaches 3 plus. Well, what do we get? 2. 3 over 3 plus 1 equals 2.
Gotcha, okay.
Okay.
That makes sense.
All right, so now what about here? As x approaches 3 from the left,
It's 0.
we would be up there, wouldn't we? Right? So this would be,
Zero.
The limit does
Good,
not
yeah.
exist.
But how do you know it's from the left when it's less than 3?
exactly.
Wow. What is this?
So they don't agree, so the limit doesn't exist. Make sense? Okay, good. All right, how are we doing?
Sorry.
We have 5 minutes.
5 minutes is all?
Can we do one where it's like the signs on the top and it's over something?
Oh, like sin x over g.
Oh, yeah, I got you. Okay, yep.
This has been an enlightening experience.
Good.
Yeah, I don't know.
So Cammy, you mean something like maybe, I'll give you an example. What if we did,
Like signs.
okay, yeah, so what if we did sine x squared? This is a real common one you see on math textbooks, math tests a lot. Okay, something like that, right? Okay, first of all, whenever you see, and we're going to do, I'll say this every time. Well, you tell me, put the words in my mouth. What would I tell you to do first with that sine function?
Square x to take your time.
Oh, how do you get all that? Jan, you got an idea?
Don't we have to do it to where sine theta over theta equals 1?
Okay, good. So what I would say is I would always say add the implied parentheses,
Yeah.
right? So the implied parentheses are there, right? It's the sign of the argument x squared. Good. So we need a theta. Now the trig limit, the special trig limit that we're trying to get out of this is one of those two that we talked about earlier in the year, right? This is the one where we want the limit of sine theta over theta as theta approaches 0, we recognize as 1. Okay, so what's our theta going to be here? And there's a definite right answer to this. It's not x, it's x squared, because whatever's inside the trig function has to be the theta, right? So what we need then is we don't have a theta on the bottom, right? We can't square the whole thing because that's changing our answer.
Let's take the square root of the top.
All we can do is multiply by 1 in this case, in the form of
X squared over x squared.
x over x,
Oh.
right? Because we've already got an x on the bottom, right? Would everybody agree?
Yeah.
Okay, hang on, we're out of time. Would everybody agree if I multiply by x over x, on the top I'm just going to get x times that sine function. On the bottom, x times x is x squared.
So it equals 1.
Good, so now we've got, look what happens. Now we've got our theta. All we need is to make that an x squared, which we can do. That's fine, because we know that as x approaches 0, what's x squared going to approach? 0. So that's a freebie.
If it was like this, it's 1, right?
So then our answer is 0. How come?
Because of the
Every
x.
time the x.
You put
Because
a
of that
0 in
guy,
and then it's
right?
0.
I've got the limit of x times sine x squared over x squared, right?
Yeah.
As
X squared approaches 0.
x squared approaches 0. So what's this going to do? That's going to go to 1, but what's this guy going to do? It's going to go to 0. So I end up with 0 times 1 equals 0.
Sweet.
Woo!
Class makes me tired. So much math to do in so little time. Yeah, I know it. What's that?
How do you think we
Oh,
stress,
no.
depressed,
Oh, I better take roll too.
stress,